So here we go. Okay, good morning, everyone. Thank you so much for joining us today. Really appreciate your participation. As you can see on the screen, today we are talking about HRVs and ERVs. My name is Jess Hoover. I am the Climate Action Director for the High Country Conservation Center. If you're not familiar with HC3, we are a resource conservation nonprofit based here in Summit County, and we have been very involved in supporting the community's new sustainable building codes. And one way that we do this is by hosting workshops like this one. As a reminder, in addition to today, we have one more scheduled thus far this winter. That's going to be March 30th with Robby, who is also on your screen with us today. And we are going to be talking about continuous insulation. It might be just the beginning of a conversation on continuous insulation. I think we'll probably be having more discussions on that in the future. And then we are actively planning more workshops for you. So if there is anything else that you want to know about related to building science, green building code, the Zero Energy Ready Home Code, whatever, please don't hesitate to let me know. All of the workshops we have planned thus far, the topics have been based on feedback that we have gotten from you in the building community. We want all of this education to be relevant to you. So if you let me know, I will find speakers, we will bring them up, and dive into all of your burning questions and challenges, whatever. So I'll put my email in the chat so you have it, so you can email me, or you can put your ideas in the chat too. And then I'll also put the sign up for the continuous insulation workshop in the chat as well. So if you haven't registered for that, I'll make sure that we have that link in there. And then March 30th is the date for that. And it is currently planned to be in person. I know that I have promised burritos for the past two workshops, or no, actually only this one so far, and I'm not delivering. So I'm really hoping, fingers crossed, that on March 30th, we can meet in person, give you breakfast, and talk about continuous insulation. Let's see. We are recording this webinar, and the recording is going to be sent out to all of you afterwards. I also owe everybody the recording for the last webinar too, so I will send them both out together. We do want to encourage questions and discussion. So as Joe mentioned, as everyone was joining, please feel free to use that chat feature. I will be monitoring questions. So as we go along, we'll make sure that we get your questions answered. We'll have a Q&A time at the end to answer questions too. So definitely please use the chat function. And with that, our presenters today are Robby Schwarz and Joe Medosh, and both are building science experts. So I'm going to turn this over to them to let them introduce themselves and dive into our presentation on HRVs and ERVs. So take it away, Robby and Joe.
Great, thanks so much. Again, as you can see on the screen, I'm Robby Schwarz. My company is BuildTank Inc. We're a building think tank and applied building science consultants here based in the Denver metro area. You probably, some of you might recognize me because I've been doing a few of these presentations, and look forward to chatting with you guys more. Luckily, we also have the pleasure of Joe Medosh joining us today. So Joe, why don't you introduce yourself?
Yeah, thanks so much. My name has been mispronounced constantly my entire life, so thank you for getting it right, Robby. That's great. I don't hold it against anybody. So I am a healthy building scientist, similar to all the building science concepts that you guys all believe in and know, but I decided to adopt the healthy side of that because somebody who says they're a healthy building scientist, and you're free to use that as you wish, somebody who's also really focused on ventilation strategies, and actually the materials that we keep putting into our homes, which clearly complement each other. And we keep adding more and more stuff, making homes tighter, and we really have not really accepted that we have to ventilate these homes more than just, as I described, a fart fan or maybe some supply somewhere in there. So we did do, I think, a really thorough job providing a lot of great information today. I have just switched from being a healthy building scientist to also adding that I am now with MeasureQuick, It's basically an app that works with a lot of wireless tools to determine if your heating and cooling system is at its optimum efficiency, because the one contractor that makes your homes healthier is actually the HVAC contractor. So I'm excited to have bridged my gaps into more people that may be interested with that on the line. I gladly will follow up later. Thanks.
Great. So we're just going to dive right in. I'm going to turn off my video so that you don't look at the side of my head while we're talking. Then I'll turn it back on as we move forward here. But again, utilize the chat if you have questions as we go along. And as Jess mentioned, at the end, we'll also have time for questions and whatnot. Here we go. So our plan ahead, you can see we have a pretty full schedule here. We're just going to dive right in. You can get a little quick overview of what we're going to be talking about on this slide. Okay, so one of the questions that is often comes up with regards to applied building science is, why are these houses that are 100-year-old houses, how do they survive? Because they're often very drafty, uncomfortable, but they're incredibly durable. So maybe you could type in the chat why you think these houses are so durable. And while you do that, I'll also answer the question. So the really big thing that we need to think about is that our expectations for our houses have changed a lot. But in the past, comfort and may not have been the biggest thing on our mind, or basically our understanding of comfort was pretty different back in the early 1900s than it is today. And that leads to this change in expectation. So these houses were drafty and uncomfortable, yet they had tremendous drying potential because so much air was able to move through them. We've changed the way that we build to meet these changing expectations. And so we need to really understand how moisture flow works in our houses differently now, and how air moves through our houses differently now. And we don't have the same drying potential as we had in the past. Some of these expectations that we think about today as comfort, efficiency, safety, health and indoor air quality, durability, all come down to changes that we've made to the building thermal envelope and to the structure in itself in order to meet these changes in expectations that we had. In the early 1900s, our grandparents, were probably willing to put on a sweater in the wintertime. And in today's world, in essence, we want to be able to walk around in our underwear from room to room and floor to floor and be comfortable. And so this notion of building tight and ventilating right really needs to be wrapped into our consciousness as we are building these new high performance homes that we want to last 100 years as well. So you'll get this question all the time, and you've probably seen this before, but the reality is that no, we can't build too tight. We've been asking the wrong question all these times. It's all about how we gain control and predictability. And in this case, control and predictability of airflow inside of our houses. So we need to build tight. And in reality, we need to build as tight as we possibly can in order to gain control and predictability. And this becomes really important when we start talking about ventilation in particular, because the tighter that we build, the more efficiently and the better performance of those ventilation systems that we'll get, which brings us to the real question, which is, can our houses be underventilated? And it's pretty much a resounding yes, that our houses continue to be underventilated, especially as we're building tighter structures. We need to deal with ventilation in a different way. And as we change the materials that we're bringing into our houses, which Joe will talk about a little bit more later, it becomes more and more important to ventilate our houses. And then now with our COVID era, there's another issue that is brought up with regards to ventilation. So this mantra that we're talking about, kind of building tight and ventilating right, again, becomes really important. And when we start talking about ventilation, we're talking about air movement. And we need to understand that air isn't smart. We used to ventilate by opening windows and expecting that air is going to come in on the right side of this house and leave through the left side just by opening windows. And the reality is that air doesn't know to follow the arrows here. It's going to take the path of least resistance, and it's going to move in ways that we often don't predict here. What we do know about airflow, though, is that a cubic foot of air, or in essence, our building thermal envelope captures a certain amount of air, and we measure air in cubic feet. And we know that if 1 cubic foot of air goes in the house, that a cubic foot of air has to leave the house and vice versa. So air in equals air out, and air out equals air in. And a cubic foot of air, just from a size reference perspective, is about the size of 4 basketballs there. So you can measure that. We measure it with blower doors and other devices, air going in and air going out of our houses. The other thing with air leakage is that there are some constant forces that we call effects on our houses that affect how air goes in and out of our houses. So wind is pushing, creating a positive pressure on one side and a negative pressure on the other side, the leeward side of our house, and air can go in and out of our houses in unpredictable ways. We have stack effect, which is just describing how air moves when it warms. It rises as it warms, and it's carrying that heat. It's not the heat itself that's rising, it's the air that's rising. And then the mechanical effect is dealing with fans from HVAC systems or bath fans, kitchen hoods, laundry, all these different fans that were creating different pressure differentials around our house. And one of the things that was is often pointed out is that these things are happening simultaneously. So it's really complex inside these houses. You might be able to determine that one of these effects is more predominant, but the wind doesn't blow all the time, but the stack effect is pretty much happening all the time. And then the mechanical effect is happening periodically as we turn fans on and off throughout the day and the year and whatnot. So understanding that helps us a little bit more. Just to bring this into a code perspective, the code is helping us define the building thermal envelope as these assembly of things that's creating this boundary condition between conditioned space and unconditioned space. And as we build better defined continuous building thermal envelopes and air barriers, and we understand the different control layers that we are putting into that envelope of our house, we're going to be able to have better performing HVAC systems and better performing ventilation systems in our houses, because we ultimately are gaining better control and predictability. And we're going to be focusing on air and ventilation today, but really that control and predictability is greater than just that. We're also talking about thermal flow and moisture flow, as well as airflow, and gaining that control and predictability. And we want that defined continuous building thermal envelope and all the integration of the different 4 control layers in order to be able to get that control and predictability in our house. Now, ultimately, we're talking about ventilation and why we need to ventilate. And so we often say that we're providing fresh air for the occupants, but as Joe often points out, we're providing outdoor air, and that outdoor air might or might not be fresh. What we do know is that there's a saying that the solution to pollution is dilution, so that in essence, the air outside, there's greater dilution of the pollutants in that air. So in essence, it's a little cleaner potentially, but with fires and other pollutants that are happening outside of our houses, that air might not be fresher than the air inside, but we're also bringing in lots of particle boards and other pollutants from carpets and other things inside of our houses. So we need to supplement the air exchange and potentially freshen up that air. Ventilation also potentially removes odors and dilutes those indoor air pollutants that I was just talking about. We get some control over relative humidity, potentially, depending on the type of ventilation that we're using. And again, we often get this question of, I'm building my house really tight, but you're asking me to cut a hole in that envelope and to bring in air from the outside. And again, that is all about gaining control and predictability of the air that's moving in and out of our houses. We can do a lot with that air if we can control that air. Now, I'm going
to chime in real quick. So,
please.
Paul Raymer is a good friend of many of you, maybe out there, and us also. And he has many books on ventilation, and he has a strategy that he describes as the solution to pollution is dilution distribution. So it's kind of a rhythmic thing. So everybody together, ready? The solution to pollution is distribution, right? So yeah, the concept is that you can dilute, but if you're not actually making sure you're getting good mixing and actually using that air that you're trying to control throughout your structure, then it doesn't help to just throw it in one area and hope that it goes to another.
Perfect. Great. Thanks for adding that. And again, jump in whenever you want. With regards to some myths, we often hear that HRVs are only work and only are supposed to be installed in cold climates. HRVs can't be used during the summer because of the heat recovery part of it, and that's a myth. ERVs are only for warm climates, which is also a myth, and ERVs can't be used in cold climates, which we're going to show you today is one of the biggest myths out there. And there are definitely some strong reasons and rationale why we want to use ERVs in cold climates. In humid climates, the ERV acts as a dehumidifier. I know we're not in that humid climate, but we want to make sure that we're covering some of these climatic issues. So you'll see some references to other climates than cold climates throughout the slides as well. And then energy use is reduced when using an ERV or HRV. The reality is that ventilation uses a motor, and that motor uses energy, and energy use is often increased when you're talking about ventilation and actually ventilating the house correctly for whatever climate zone or house size that you're working with. Now, there's some problems with ventilation as well, and it goes back to this notion of air being a transport mechanism. Air is a transport mechanism that moves moisture and heat around our house. So it's exchanging moisture and heat from inside and outside, even when you're not bringing it through a ventilation system. And we talked about the stack effect and wind effect and mechanical effects on houses. That's how it's moving it. So again, gaining control and predictability of this ventilation flow and normal airflow in our houses becomes really important. So we're exchanging, from a ventilation perspective, relatively clean air from the outside to the inside, and vice versa, taking relatively, what we're calling dirty air, in essence, from inside to the outside. But remember that's not always the case. So you might need to disable the ventilation system or change the ventilation rate depending on outdoor and indoor conditions in that house. And then continuously reconditioning that airstream potentially can happen with ventilation systems, but it's not all ventilation systems that can do it. There are some things that we worry about ventilation: heating, cooling, humidification, dehumidification, filtration. All of these things aren't a given with specific ventilation strategies, and you probably can't, depending on your house's building envelope and whatnot, actually heating and cooling your house with just a ventilation system is not something that most houses can rely on there. So you want to pick your ventilation system for your particular structure there. When we get into the heat recovery ventilator, we are moving air in and out of the structure simultaneously, and that's why we call them balanced systems. When we're talking about balance, we're really talking about pressure balance inside and outside the house. We're not creating a negative or positive pressure inside the house if that system has been commissioned correctly, and we'll talk a little bit more about commissioning here. Within HRV, we're exchanging also exchanging energy across the core. And we'll talk about how that happens. And that energy is called sensible heat because it doesn't also include moisture heat. And that's where we get into the energy recovery ventilator that's also moving air from inside and outside. It's also a balanced ventilation system that gives us pressure neutrality across the building envelope if it's set up properly. But it's able to move what we call the sensible heat, like the heat recovery ventilator, but it's also able to exchange moisture, or what we call latent heat, across that core. It's designed to help keep the indoor humidity levels at a certain level. So it's able to exchange moisture dependent on where the moisture is more pronounced, or there's greater concentrations of moisture. So if there's greater concentrations of moisture inside the house, it will exchange that moisture into the indoor, the air coming into the house. If there's greater moisture outside the house, it will be able to move that moisture into the exhaust airstream and keep that moisture out of the house. So this is just a hint, I guess, that it can work in different climate regions, not just the humid Southeast, for example. There are new generations of ERVs that can also heat and cool our houses. We're not going to talk that much about them, but again, it's really dependent on your building type and building thermal envelope, whether these new types of systems will work with your specific building envelope and house that you're designing there. We just wanted to make sure that you were aware that they're out there and they're available. These new recovery ventilators plus conditioning ventilators actually deal with a lot of other things as much as filtration and dehumidification, as well as heating and cooling our houses. And there are a couple examples there. The CERV CERV has been around for a while. And then there's this other one, are examples that you could look into. Again, they can do other things than just ventilate, but you need to have great connection and continuity with your building if you're going to rely on it to actually heat and cool the house as well as dehumidify.
Robby,
I want to add that, yeah, go ahead. Yeah, go ahead and ask your question.
Yeah, so I just wanted to say that we had a question come through that I want to make sure we answer before moving on too far.
Sure.
Stephen asks, isn't there, I hope I say this word right, isn't there an enthalpic membrane not shown in the ERV picture?
Go ahead.
Yeah, it's actually in the core materials itself. Some have a desiccant concept, but most of them have kind of faded away from that. That it's embedded into the membranes that are across a part of the core, or the membrane itself is actually built out of materials that are allowing the moisture to flow through that as one flow in is moving across the other one out, that they're able to transfer that moisture from both sides. That they really have gone to a very sophisticated materials that are being used in the cores today to try and move that moisture from the high to the low.
Great. Thank you.
And you want to add anything else?
Yeah, I do want to add. So that these serve to, or the Minotaur, these are conditioning, and they would work for a small envelope or a small footprint. They're not intended to be the complete conditioning for the home, but they are trying to provide supplemental conditioning of the air that's happening. They also do a great job of just, I don't need to bring in fresh air because I'm monitoring it. I will just recirculate what you have because it's doing fine. So they're able to be super smart about how they use the indoor and outdoor air based upon what's going on inside. So they have a lot of really high-end sensors, and they have a lot of great intelligence behind them to actually make the best out of what these devices can do.
Yeah. And like I was getting at, they're probably more appropriate for a passive house type envelope as well. So you're gonna need to make sure that you understand the loads that the house is receiving, and if the system can meet the loads by itself. That brings us to, how do you learn more about these systems? The HVI certification process is a directory of different systems that are out there. They have a method of comparing the ventilation performance and certifying the ratings, the performance of these different systems out there. It's a great tool to learn more about the systems that are out there. So we wanted to bring that up as well. Oops. Okay, so we're going to get into the heat exchanger core here. And Joe,
Sure.
did you want to take
Yeah,
off?
sure. Sure. All right. So, although there's lots of pictures of cardboard here, these coils are not actually made of cardboard. All right. And they're doing a great job of trying to take air from that's coming from outside in and basically heating or cooling it or conditioning it with the air that's inside that comes back out. And if it's an ERV, it's also exchanging the moisture content that's all in there. So these are super fine. These things are actually getting much more elaborate as to how thin these types of coils are. So your core can actually be, many of them are square. We'll talk briefly on the next slide about that, but you're basically mixing two streams without actually touching each other. They're able to, again, transfer their heat or cooling and moisture at the same time. These can range from 50% efficient to something 95, and we'll talk about the differences here. So the one that's very traditional and you see in most of the units and most of the illustrations is a cross flow heat exchanger, right? So clearly the supply air moving through one way and the exhaust air is moving the other. That's what transfers all the conditions, but these usually have less of an efficiency. So again, you can get above 70, but in general, most of these kind of units are around 70 to 75. There are some units now that have actually been able to achieve 80 to almost 85% efficiency, meaning that if you had 100-degree air moving across and you had 60-degree on the other side and you transfer those, you're going to be able to get an 85% transfer of that. So you'll end up with, I'm sure there's some better math and I'm trying to do it in my head, but you could end up easily with, instead of bringing in 100-degree air, you're probably only bringing in around, let's say, 85-degree air. So that's kind of the concept, is that the higher the efficiency, the better I'm able to transfer and not lose heat or cooling on either side of your envelope as the air moves. So these can be very small. These are the small units you may see. We're not here to promote anybody, but Panasonic, for one, makes a very small, I call it the hallway unit, that's trying to be, it does great for trying to comply with ASHRAE 622. They only do around 40 to maybe 50, if I think, CFM. But in order to do that, you got to have a very small core, and that's the kind of core that's just described here.
Yeah. And because I put the cardboard in there, I just wanted to point out that if you look at the core picture here, it's like that corrugated cardboard. So the airstream goes through each of the corrugations there, but the two airstreams never touch each other. They just, the corrugation gives it the ability to exchange across it.
And then there's others that are called counterflow heat exchangers, where you can see, I left the crossflow here up on the upper right corner, and now you see the counterflow, which is very, it's octagonal, and it usually gets elongated, trying to allow you to have more surface area to exchange that. So these can actually get up to 94 to 95% efficient. The challenge is that the more efficient one of these cores are, the greater risk you are to actually freezing in a northern climate. So if I'm only exchanging 70% of my heat capacity, then I don't, when I'm bringing in cold air, I actually don't have less of a risk in actually freezing the coil than I do with actually a counterflow type of a style. We'll talk about how to supplement that with other methods, but just in general, this is your risk. So if you were in a semi-mild climate that had severe cold weather, counterflow probably has the risk of freezing up if you didn't have other supplemental methods to either heating or some type of defrost. So at the end, we're going to talk about here the things you're asking for or looking for. So these also come with a price. You can clearly see that the cross flow is probably a more economical option, much more common versus the counterflow that's out there. So you should know what kind of core you're getting and what are some of the requirements that go along with that. So ERVs do everything that an HRV will do. Instead of the basic aluminum heat exchanger, they have this polymer core, and now they're getting very elaborate in terms of a desiccant that's already embedded in them. So they're able to absorb and transfer that moisture that's there. And again, one of the things that people forget is that if you have high moisture inside, that you're able to keep it inside with an ERV, and it doesn't dry your house out. So these are some of the things that are making ERVs much more applicable all across the country. Again, we're getting rid of the myth as to you only put one type in some areas and not the other. So we really want to make sure that's the takeaway today, is that an ERV works well in a cold climate.
Great. So we're moving to talk about a little bit about the efficiency of these units. And as Joe was saying, the HRV, the average efficiency is 70, but it's often thought that that's considered the low range of it. And as he was mentioning, depending on the core and other characteristics of the system, you can get sensible heat recovery that's up in the 85, potentially in the 90% range as well. Now, the sensible and latent heat recovery for the ERV is that kind of average in the 40 to 60% range. I don't believe that there are many that are much higher than that 65% area potentially out there. Moisture control for ERVs is one of the biggest differences there, and that we understand that moisture, like heat, basically is moving from these higher concentrations to lower concentrations. Just like heat is moving across our building envelope based off of the delta T temperature across the building envelope, moisture is moving across depending on the moisture pressure across that pressure plane or that building envelope there. So if you have higher concentrations on one side than the other side, you're going to have a moisture drive in one particular direction there. So in humid climate zones, ERVs don't really lower the indoor humidity. It can actually increase it, but the issue in that climate zone is that the HRV would make it even worse out there. So moisture goes up, but the stale air is ultimately exhausted out of that house. And so in those climate zones, you would still need some level of dehumidification, probably because you're bringing in substantially more moisture from the outside into the inside there. In our cold climate, however, we generally have more or higher moisture levels inside of our houses than outside of our houses. So the moisture exchange is going to be from that airstream going out of the house to the airstream going in, and you're able to keep a percentage of that moisture. Some of it will be exhausted to the outside, but you're able to keep a percentage of that moisture and keep a better level of moisture inside the house for the occupants, for the finishing materials and those types of things. Now, regardless of the systems, you really need to maintain those systems. ERVs have a little bit more maintenance because you're dealing with moisture, and that moisture attracts particulates and other debris that's in that air. So they do need to be cleaned. The filters need to be cleaned. The cores need to be cleaned. ERVs and HRVs alike need to be maintained here. And then there are different levels of filters that you can put in these systems as well. In a lot of the systems, they'll accept a MERV 13 filter now. And what's nice about the MERV 13 filter is that it can filter out viruses as well. But you have to understand that this is filtering the air that's coming in from the outside. It's not meant to filter the air that's already inside the house like a traditional HVAC system does there. So from a health and safety perspective, it's not really designed for that filtration of the air inside the house here. Now, as we said earlier, historically, the HRV has been kind of regulated to the northern colder climates and the ERVs to the hot humid climates. But a lot of experimentation and building science research has really proven that that's not the case anymore. That Although you probably aren't going to be using an HRV in the warm, humid climates, the ERV actually can be used in a lot of these northern climates until probably you get up into the Arctic. Maybe that would be an area where you might not want to do it.
They are used in Alaska. There's a lot of threads, and you can find a lot of good people that are putting them in Alaska. So it's clearly not limited by, maybe the North Pole may be an exception, but Alaska, it's not uncommon for people only to put in ERVs.
Yeah, good point. What we know is that cold air it basically holds less moisture than warm air, and then in the winter we have very dry, and in our climate zone, it's maybe even drier than like on the East Coast in climate zone 5A. We're in climate zone 5B, that dry section of the country. And so the ERVs help again to salvage that moisture that's moving from inside the house to outside the house and being carried in that moisture transfer mechanism with air. And so we're able to actually hold on to some of that moisture and move it back into the house there. So again, the moisture is moving from higher concentrations to lower concentrations. So the incoming air has lower concentrations of moisture, and therefore it's able to transfer across the core to that incoming airstream and help maintain the moisture content inside the house in cold climates here. Again, they work very similarly to an HRV, but we're adding that moisture transfer as well as that heat transfer there. So in the heating season here, this box is basically talking about that core component of the ERV that makes it beneficial to consider using in a cold, dry climate, is that we're able to return that moisture back into the house and keep that moisture content pretty constant inside of that house. And you can see what's happening on the other side where it's being exhausted to the outside. That's in other climate zones that we're talking about here. So humid climate zones, obviously an HRV is not a great idea. We're going to be pumping that moisture in, but in our cold climate zones, because we don't want to dry out the house as much in the wintertime, we really are starting to see ERVs being used to a great extent in these cold climate zones. So this HRV versus ERV in specific climate zones is really not as pertinent as it used to be there. Sometimes we think about where's the best place to put these equipment. Tight houses, high occupancy loads. These are areas where moisture content might build up naturally inside that house. So if you want to keep that moisture content inside that house, you want to deal with, or you want to consider using an ERV and ensure that HRV choice is probably going to dry out that house, even if it's a super tight house and you have occupancy lows in our climate zone. An HRV is probably going to be a poorer choice from a moisture perspective inside of that house. But we wanted to let you know that there are some other devices out there, HRVs and ERVs that are ductless, that are small, that are through the wall type components here. There's the Panasonic's Whisper Comfort, that's a smaller unit. Generally speaking, these types of units are used in small dwelling units. So in apartments, in auxiliary dwelling units, in condominiums and whatnot, you might choose a unit like this because they're easier to install. You don't have to find space for them. You don't have to run as much duct or any duct. So we're not going to talk a lot about them, but we just want to make sure that you're aware that these types of units are available. And again, primarily used in smaller dwelling units.
I'll add one more thing to that slide though. And one of the concepts that people say you need balanced ventilation doesn't mean you need a one unit that does balance ventilation based on the code and other compliance pathways. That you must have, in theory, an exhaust fan and a supply fan that are, face value within 10% of each other. That is technically balanced ventilation, but you can imagine quickly that I'm not getting any kind of conditioning. It's difficult to confirm that they're controlled together. So there are ways that people think about, like, oh, I can put balanced ventilation in, and as all they're doing is a supply fan and exhaust fan that, are all from the similar switch or from similar controls. But you're going to find out quickly that that's not really the most controllable method. And for cold climates, I wouldn't even think of it actually as a realistic solution. So some of these ones here, the Lunos is I could describe it as a pretty cool solution, but it's designed to be like 15 minutes out, while the other one 15 minutes in. They're together, then they actually reverse their motors and go the opposite way. So I think they would be challenged in a super cold climate to not freeze, but also just be bringing in super cold air. Many of you guys are minus 19 this morning. I don't think they were intended, or some of these are intended for that type of climate. So make sure you're aware of the limitations. If you're trying to be conservative or alternative, you may find that you regret that choice.
Great points. We're going to move into distribution of these systems. So if you might have noticed that most of I think all the units basically have 4 ports on them. And 2 of those ports are bringing air. One is bringing air into the house, and one is bringing air out of the house. So when you try to duct these systems, the simplest way is basically a single point supply and a single point of exhaust inside the house. But we need to remember that that's probably the worst way to actually install the system, especially thinking that your house has bedrooms and doors and things, and that it's easily able to disconnect the exhaust or supply side from being able to see or exhaust or supply to the entirety of the house there. So generally speaking, we don't like a single point supply system. A multi-point system is able to distribute. Generally, we want to distribute the incoming air to bedrooms and main living areas, and exhaust from common areas that are like kitchens, bathrooms, these more polluted sources. So a multi-port system is one that works a lot better in order to distribute and exhaust air from our houses. Some systems use the air handler ductwork as well, which gives you a little bit more reach around the house to distribute air and to exhaust air from. But often in our cold climates, as you know, we're not using forced air systems. We're using hydronic heating systems. So you're going to be talking about ultimately ducting these systems. So a fully ducted distribution system that is done well looks something like this. In this case, we are ducting the supply, which is the blue side of the system here, and you're offering at least 2 supply ports, one to bedrooms and one to the main body of the house. And similarly, you're exhausting from 2 locations, at least one from the bathroom and one from the kitchen location. So you're taking substantially dirty air, what I call dirty air, high moisture content, potentially air as well. But if you're using the ERV, you're able to bring some of that moisture back into the house and distribute it well. Now, there are other ways. If you have a forced air system, we're not going to spend a lot of time here. But the big thing if you have a forced air system is really pointed out in this picture here. Oftentimes, when an ERV or HRV is ducted with a forced air system, you end up bypassing the true ventilation process here. So you want to make sure that you're installing, if you ever have the opportunity to install a system in conjunction with a forced air ducted system, that you're not getting this bypass and the ERV or HRV actually not contributing to ventilating the house at all. Now, there are other systems out there that are packaged units, packaged systems that include a distribution system. This is a Zender system that has a manifold technology so that you're able to supply and exhaust air in multiple locations rather than self-ducted systems where you're building a duct system and it's really hard to take exhaust air from more than a couple locations, and similarly to supply air to more than a couple locations. In this case, if I have a 3 or 4 bedroom house, I can supply air to each of those bedrooms as well as each of the common areas, and I can exhaust. Maybe I can exhaust from more central locations or in other ways, but it's a great system. And they work really well. And the other nice thing about this type of system is that it comes with these balancing dampers on the supply side. So this is that manifold duct that's coming to a supply register, and you can turn this register here and adjust the airflow. And as Joe's going to be talking about in a few minutes, it's super important to commission these systems to ensure that you're getting the right airflow in each location, and also the pressure that's associated with that in each location. Operating cost is another thing to be thinking about. Balanced ventilation systems are generally a bit more expensive than traditional supply and exhaust systems, but they can also lower your operating cost. Traditional supply and exhaust systems, the main thing that we're looking for from an operation and cost perspective is how much watt draw there is for the specific fan type. And that is something that you want to look for in ERVs and HRVs as well, is what is the watt draw of the motors and fans that are being used inside those boxes there. There are some low watt draw systems. This Venmar one, for example, is 13 watt draw. So it's going to be more economical to operate. And depending on if you're operating it continuously for continuous ventilation or intermittently, that your cost of operation is going to obviously vary from those different run times there. Now, which should you choose? Well, for small and tight houses in cold climates, a lot of people choose HRVs, but you want to choose them wisely. Make sure that you have a house that, and I guess the first reason why you might choose it for a small tight house is that tight houses and small houses, just in general, the moisture level is going to increase. And if you have occupants that have multiple people in a smaller house or a lot of plants in a smaller house, you might need to do some moisture mitigation in that type of house, even in cold climates. So an ERV is going to help dry out the air. And so in essence, if you have too much humidity in that house, which generally happens in smaller houses, you might choose an HRV over an ERV. As we've, I think, been pointing out pretty regularly here, ERVs are not excluded from being installed in cold climates. But in general, we're seeing them installed in larger houses in cold climates there to help maintain the humidity level, the moisture level inside of that house. There's some hot, humid climate and mixed climate concerns as well that if you ever build in those climates, you want to look at. The HRV is definitely more efficient at transferring heat. So if that's your main concern, you might choose an HRV over an ERV. The ERV is transferring moisture but also heat. Again, it works well in a cold climate, but you want to think about the moisture load in the house that you're creating as well. There's still all kinds of questions that you should be considering there, from climate to efficiency considerations, watt draw, the ventilation rate, and then installation considerations. Are you going to actually be able to use a multi supply strategy, a multi-X exhaust strategy in your houses, and can you run duct in that houses? When you're talking about an ERV or an HRV in a cold climate, we need to think about, how experienced are we at running ductwork in those climates, and what system can we choose that's going to make that an easier transition, because it's quite different running duct versus piping for a hydronic system there. We need to think of the flow considerations and whatnot, and Joe's going to get into that here in a little bit. Joe, do you want to talk about frost?
Yes, I am. I am to make sure I'm unmuted. So some of the conditions we're trying to compare are, we have outside air that's coming in at very low temperatures, low moisture, but we're adding the moisture from inside. So now we have the ability for things to freeze, and sometimes freeze rather quickly. So one of the things you think about is that how far in the house is the actual unit in the core compared to where the outside air is coming from, and how much condition does it get indirectly from the house, and it actually is being warmed up as it gets to there. So you can think about that it's super cold outside, but what's the temperature in your garage versus what's the temperature in your house? And you may find that you're thinking that it's minus 10 outside, but the reality is by the time it gets to the core, it may actually be 30, 40 degrees. And there's other things we can do to reduce the frost that could build up. So there's a variety of things that are preheaters that we'll talk about here. I don't know if I have the right order, but we have there is a threshold that we're showing here, since ERVs transfer the moisture, that the temperature goes higher, right? So if your indoor relative humidity is 30%, your frost threshold is 23 degrees, or your ERV is now down to 4 degrees. So there's I think part of the question is I would want to understand more about exactly what you guys are having. So on today's like today, you may find that your system actually runs on a defrost mode for a large portion of the day, so that there is times where what it does, it'll just no longer exhaust. So it's not actually, it's just trying to provide air from inside to outside. So I'm not bringing air inside. So you're like, okay, I'm exhaust only. So I'm really not getting the exchange that I thought of, that I'm paying for. Sometimes it may only be 5 or 10 minutes out of an hour. It could be as much as sometimes 30 to 40 minutes an hour, depending on the conditions outside. So this is your recirculating approach that you see here, that where, the air intake is just, I'm only taking air out. I can't afford to bring air in, not just from the expense-wise, due to what it's doing to the coil, and I don't want that to freeze up. Some of them will just actually just kind of shut down. They're like, okay, you have exceeded the threshold. I now have to stop working for a while, and when it warms up, I can actually now recondition the air and continue to work as normal. Some other ones also have the ability to have a heater on them, so that you can also have something that is designed to actually provide a resistance heat on the outside. Some of these have this and they're built in, you're not even aware of it. So the question is that if you're after efficiency in terms of how much energy you're using, you've now lost. But the question is which one are you rather pay for? Getting regular air from outside in exchange, and making sure your system is working thoroughly, and not the coil either freezing up or only doing exhaust only mode. But it's going to cost you a little more money, similar to people who have using heat pumps, and they have electric backup heat, that they find that there's many days of the year where they're actually paying for resistant heats, which is incredibly expensive, versus being able to use the best components of that heat pump. So yeah, go ahead. Yeah.
Just to recap, we have the recirculation mode. So you're not taking any air from the outside. You're just recirculating air from inside and keeping that core warm. You have an exhaust only mode where you're exhausting air from inside to outside across the core, again, keeping that core warm so it doesn't frost up. And then you have this electric resistance, which is obviously a higher energy penalty because you're adding more energy to the system there. Sorry, Joe.
That's right. That's good. Yes, right. So Hopefully that answered the question. There are some questions that I see here, and we're going to address those on things that are coming up or address them directly. So we are letting you know we are seeing your questions.
Okay. So the last thing that I wanted to just point out, and then we'll switch to some other issues that Joe's going to take over here, is with regards to performance and how performance is measured, so that when you're looking for systems to install in your house, you want to look at the sensible recovery efficiency, the SRE, the adjusted sensible recovery efficiency, and the apparent sensible effective efficiency. These things can be found in the HVI listings. You can find them in the product manufacturers documents as well there. So this is kind of how it's measured, and it's measured in a percent range, and the higher the percent, obviously, the better it is at doing these recovery. You can see an example here for HVAC performance. We have the power consumption. So again, it's really important to look at the watt draw of it, especially with regards to your DOE Zero Energy Ready Home program code. It's partially, you partially demonstrate compliance of that using a HERS energy rating index, and the watt draw of the fan and the runtime of those fans can impact your ability to get that threshold HERS index score that you need. Same with the sensible recovery efficiency as well. And remember what Joe was talking about is that the higher efficiency it is, potentially in cold climates, the greater the frost potential in that system is as well. Now, ERVs have a couple other efficiency measurements because of the moisture transfer that's going on. So we have total recovery efficiency, adjusted total recovery efficiency, and latent recovery efficiency. So that's specific for the moisture transport mechanism there. When you look at them up, you'll also get the power consumption of the fans here. And then you can see the sensible recovery and then the total recovery efficiency of these units. These this is information that you'll need to pass on to the energy rater who's doing the energy model there, so that they can input that information. But it's also information that you should be considering when you're choosing the system that you're going to be putting into your home.
So one of the things that probably will hit the press, I'm hoping fairly soon, definitely this year, is that a good friend of ours, I mentioned earlier, Paul Raymer, with our distribution phrase, is working on a concept called the ventilation manual BV for balanced ventilation. So it's similar to the manual J concept and complies with what ASHRAE 62 is requiring, and usually tries to get you a little more over that threshold. So I did want to reach out to Paul for thanks those, and do reach out to Paul if you see him on LinkedIn or Facebook. He is actually a novel writer who writes with building science as the key culprit to some of the things that he puts into his novels. So it's incredibly creative writing. So do track down Paul if you're not familiar with what he does. So he describes the systems as category A rooms that are supply, and category B rooms are the exhausts. Clearly, these are bedrooms and living rooms, areas where we want to breathe, the best air, and the other rooms are where we actually are making the stale air or the contaminated air from the kitchens, bathrooms, laundries, utility rooms. So if you separate these categories, then you can actually go through a concept of, easily determining what you need in the house. And it's same as I could actually take a napkin and probably figure out how to do your house. Same way I could probably take the same napkin and draw, 4 wheels and a box on it and say it's a car. But we will be able to determine here as we go through the next exercise as to what these actually look like. So he has a great concept, which is trying to show you that you can actually do supply and exhaust in some of the same rooms. So you can see here that he's got on the bottom right, he's got the master bedroom with some supply and exhaust, because he's trying to create good balancing and mixing, distribution, dilution, all in the same room. Especially if you're closing doors a lot, then this actually makes a lot of sense to do that, because if you're only supplying and you're not allowing air to move out of these rooms, and you can see why it actually makes sense to add exhaust and supply depending on what the dominant one is you need for that type of area in terms of exhausting exhausting more contaminants or supplying more fresh air that you want to breathe. So we're going to break this down and not be so complicated. So we're just going to go through supply, and you'll see that we're going to start building out our house in terms of what we got here. The reason I use 20 is because your bathroom is required to have at least 20. That's a minimum, because we are not going to have an exhaust fan in there. Okay, so in general, depending on how you, many of these have distribution and the amount of flow that goes through your ducts. And so the Zender system has a system that allows you to do this. They refer to each one of their ducts as running probably around 12 CFM, worst case is 10, depending on how long the run is. So you want to make sure you understand the friction rate, what type of ducts are you using, large sweeping bins, you're using metal 90s if you need to, 45s are better. All the same principles as to running duct systems come into play here, because your flows are even so much smaller. These are really low flows that you need to make sure that you have accounted for the distances and the curves, bends, all those kind of things will actually come up to doing that. So here we have the balance side, all right? And you can see that our goal is we really need to find out that I'm supplying and exhausting the total. And I want to make sure that people know that in this scenario, we do not have bath fans anymore. So there is a significant savings about the bath fan, the install, the ducting, all those kind of things, the termination. But you must really put in a kitchen exhaust hood. You probably get away with it because you can actually say that I have enough continuous based upon the air changes for the kitchen area and volume. But kitchens have a lot of particulates. This is really probably one of the most hazardous rooms in our home, and we spend a lot of time there and do a lot of cooking, which is lovely to eat but nasty to breathe. So do not think that we're implying that you can get away without a kitchen exhaust hood. They compromise your system because they're taking out 150, 200, 300, 400 CFM, and hopefully you have some makeup air or you're prepared when you get that high. But even if, let's just say it's 200 CFM, your house will be slightly out of balance while you run that. Your ERV, HRV cannot accommodate that type of imbalance, but it's usually for a small amount of time and for a good reason. So let's continue this example thoroughly. So as you see now, you can see where I tried to think about a plan that if I'm going to supply in the far side of the master bedroom, I try and put them right above where people are breathing. So this would kind of be above where the bedroom or the bed would be. So I'm really kind of blowing fresh air on you as you breathe. And then in the bathrooms, they're in an area where I'm trying to grab really the most moisture or most conditions. And I tried to, you see, I'm trying to pull air from one side of an area to another. So I'm really trying to get a good balance and a good distribution and a good mixing of air. So I didn't really want to align these. And again, you're limited by what's there and what the client says. No, I don't want that thing in my ceiling. You can put it over there, but remind them this is all about getting them good sleep, good rest, good air, good ventilation provides a lot of great health benefits. And we'll find out some of the restrictions of what that statement is. So you can see here, you're starting to look at the running a bunch of ducts to these areas. This is all could be one level, but we know there's using more than one level to do this. So, but in general, you're using usually more than one duct sometimes. So if you're using flex duct, you need to make sure they're super tight, well designed, installed correctly, and you're going to commission it at the end. And you want to find out before you commission it, you put some drywall up to make sure you're getting flows, because you do not want to find out after everything is already drywalled that you realize that something's crimped, something was no longer working. So you get this. So this is what your supply is looking like. And now we actually can add the exhaust, and you can see where there's a lot of stuff happening throughout a building, especially if you start moving into multiple floors. So I tried to give you a visualization if this was a two-story house. So I'll try to break this up, and you can see now what happens when we start to move stuff up. So you can see where we're trying to create a quick distribution out. Let's get a way to a manifold that's now going to allow us to use multiple takeoffs. All of this stuff needs to be well designed. Some companies sell you manifolds that are very specific as to the amount of takeoffs it can have, and sometimes you'll need you have 3, but it actually give you 4, so you're going to get a cover for one of those. But this is just, again, the concept of let's send a bunch of stuff up to the top floor. Maybe the attic is actually well conditioned. I can use that as a great path to move around, and I'm going to do the same on the exhaust side. So this is the concept where you can see it looks very simple, not that complicated. Numbers are easy to do. And the reason that I did the bathroom at 40 was because that's where you're spending most of your time, and that's where you're going to gain the greatest benefit in terms of keeping your carbon dioxide down if you have that much flow in, and you're probably using that bathroom more than anywhere else. So I also want to probably exhaust more into that. But you could have gone with 20s everywhere and probably done fine for that. Now at the bottom, sorry, real quick, I can tell how big of a system I'm looking for. So if you find something that's around 150, that's not the end of the world. If you got something that's 100, you probably have exceeded that unless you did a bad installation and maybe you only get 100 out of the house. So you can see the napkin concept where I can easily add up what type of system do I need. Then it gets into the details as to really what do I need to do for my climate zone. So somebody mentioned, yeah, go ahead.
Well, I just wanted to mention that often ventilation rate is designed based off of ASHRAE 62.2. So then you're trying to distribute that ventilation rate around the house to your kitchens and bathrooms and bedrooms and exhausting it to balance it there.
Right. So that's why the bathrooms are always a 20. But see, it's hard to do like, oh, I'm going to do 28 or I'm going to do 30 because you're changing a lot of duct sizes or multiple ducts. So you'll need to figure out what is your system that's carrying a certain amount of CFM and what's the distance. Once you get over 30, 40 feet, you're losing a lot due to friction. So that one short run easily gets me 20, 55, 60 feet down, I'm no longer getting 20. Maybe I'm only getting 15 out of it. So those things you need to be able to fully engineer and really compensate for. So, but again, you're going to have a kitchen exhaust in here. You're just looking to remove some of the stale air that, doesn't get caught in your range hood. Somebody asked about sound, and sound is a significant issue because if you're not cautious about how these are installed and insulated, or you're getting manifolds with silencers, they actually have silencers inside them that allow you to reduce this. And these manifolds aren't in, the master bedroom closet, so you could indirectly hear them at night. So you need to be also aware as to where they're at and how they're run. And adjacent to other places where people do want to be able to watch TV without realizing that their ERV is now running constantly in the background. It's something you don't want to be aware of.
Yeah. Joe, somebody also asked if you had a approximate square footage size for these examples, size of house.
If I had to shoot quickly, I'd be like, most of these systems you see, 2,000, maybe 2,500, you're dealing with an average unit. Most average units are going to do around 120, 150 CFM. So if you're going to get above that, you're either looking at a much larger unit or actually 2 units. It's not uncommon for homes today to actually put in multiple units to get a better distribution and being able to control all of this ductwork.
So really, ultimately, it comes down to the ASHRAE 62.2 calculation for that specific house, trying to determine the total ventilation requirement and then sizing the system correctly for that sizing. It's kind of like doing a manual J first and then a manual S to size the equipment for the capacity.
Yeah, but I will try to stress that manual J, just like the code, is a minimum. That you are striving to reach the minimum amount of ventilation that you'd want in your house isn't something that I really want to strive for, especially if you're spending some good money to put something like this in your house. The last thing you want is the minimum ventilation. So I'm encouraging people to think a little beyond that. You must reach your 62.2 requirements, but most of these systems, as you see I've designed here, usually have gone past that capacity, and it's better to have a little more than to be just on the fringe of just going, I just have just enough ventilation.
Is there a maximum? And can we overventilate?
Well, depending on overventilation now comes into, am I able to maintain the moisture challenges that happen? So some areas that are high moisture areas have to supplement that with a dehumidifier, or you also can adjust the rate that these things are flowing. So most people are around 0.3, and that could increase to 0.6. Depending on the flow. So you may go, oh yeah, I have a good design, but I'm going to increase the flow that I'm getting out of them. So you do have some flexibility once it's installed. Some of them can really push the amount of air that happens through that. Others that may be a little more restrictive.
Yeah. And so that was a question that just came in with regards to controls. How are these running continuously, intermittently, and also it might be good to mention, which I think you alluded to, is the boosting modes.
Yeah. So yeah, I may have did. So let's clarify the boost mode. So we mentioned that you've eliminated the bath fan. That doesn't mean that when you get out of the bath that your mirror is not going to have condensation on it. Okay. But if you want to do the numbers, if you calculate, 24 hours at 20 CFM versus my, 80 CFM that runs for whatever time I have it on for 20 minutes or whatever those numbers are, you can see that the math works out that I'm clearly getting better ventilation that's constant. There are these switches that you can put in that would boost it and allow everything to rev up. It doesn't just rev up that area. The whole thing has to rev up. It's it's a whole system approach. But it could rev up enough to try to reduce the amount of moisture that you have without having to bring out a towel to see yourself in the mirror after you get out of the shower. But those are some of the challenges that go along with these conditions. Some people still put the exhaust fan in and still just do a boost like they do a kitchen fan. So it's not the end of the world to not have some of those things that you're using just for, point of source time use to provide a convenience, if that's really what you need to do.
Great. Another question came in, but I think we're going to hold it for just a second.
Okay. So here's one of the large misunderstandings of all the ERV, HRV understandings that people have. And I talked to lots of people in the industry. The people think that this ERV system is actually filtering your indoor air. And the only thing it filters is what comes into the house through the system. So it's mostly just keeping itself clean. It's keeping its core clean and doing that. Now you can add a filter box to improve that and increase that. You can actually add charcoal filtration. You can add large supplemental filtration to overcome wildfire smoke, but it is not recirculating in the house and filtering your air like a traditional air handler would. So on the right side, this is what we're expecting when we have an air handler. It's circulating in the air, it goes past the filter, it goes in, it comes back, it goes past the filter. That does not happen. And you really might want to be considering that you get some supplemental filtration, clarify, not purification, but just filtration. You don't need all that ionizing stuff on a unit. Just filter it, grab it, throw it away. But you may find that there's times of the year where you want to filter more particulates out, especially in the bedroom or common areas that are near the kitchen. So the one thing that this can actually be a benefit, it's not a elimination, but it can be a reduction, is when you have a really tight home and you have balanced pressures that you no longer have stack effect, and you're reducing the wind because it's a tight envelope, and because you don't have imbalances, you're not actually end up with negatives. Now you would, again, if you turn on your kitchen exhaust fan, that you put it back somewhat negative, but in general, you are making a significant reduction in wildfire smoke exposure. Now, if you had the same balanced and you had a leaky house and there's any kind of wind, I think our next slide actually adds some wind to that. So you will find out.
I just want to point out that with the Marshall fire that just happened in Boulder County, I know of a house that did not get smoke damage specifically because of its house tightness levels and ventilation control.
So, but if you got wind, whatever's outside is coming in if you have a leaky envelope. That's just the bottom line. So, and I did want to ask, so who out there can tell me what are some of the blower door numbers you're seeing? So, and by the way, 3 air changes is kind of tight. It isn't that tight, really. I mean, if you're down to 2, that's tight. 1, you've really upped your game and you've really stepped into a whole nother level. If you're below 1, you are those are impressive numbers. That's a tight envelope, 1 and below. Above that, you're really keeping some risk happening.
So we get
go ahead.
We get a answer to that average around 2. And then before we move on, let's look at this other question that came in. It's asking about that ERVs can only maintain humidity, but cannot actually control humidity as it reduces interior humidity if it gets too high.
Yeah, I remember that question. I was going to try to do it when we did the slide about the filtration. It's the same concept that it can only maintain what's going through the unit. So in general, it's not reducing, the total humidity in there, but it's not in terms of, a dehumidifier. So it's not acting as an interior dehumidifier. It's acting as the way to reduce humidity that's coming in or actually keeping it inside when the numbers are correct. So usually keeping it inside is more of it rarely is an issue, because usually it's high humidity climates that are trying to reduce it from coming in. So it's not that common where I have such extreme humidities inside. Again, it could be a small, tight home where, wow, I have stuff dripping on the walls, but that's, a factor of too many showers, too much cooking, and too many people. You may find that you still need to provide some dehumidification in the house.
Yeah. So we're going to transition just a bit and go through this fairly quickly, but we wanted to make sure that we touched on the EPA's Indoor Air Plus program, specifically for you guys in Summit County, as it is part of the requirement of the DOE Zero Energy Ready Home program and code that you're dealing with here. So
I do want to note that there were several questions that are a little complex. We will grab those at the end. Some of them we can't answer, so we'll tell you at the end which ones we can answer. So there are a few indoor air plus requirements that some people forgot about, and this one is very simple, and that is that you need to have if you have an attached garage, you need to have an exhaust fan in the garage that's designed to move 70 CFM for an hour after the garage has been vacated. I thought there was some option for occupancy or carbon monoxide, but basically just saying if somebody's in there, they want it to come on and off for an hour, because it's probably when your car goes in and out. So, or you can verify the connectivity of the house to the actual garage when you're doing a blower door test, that it should be within 5 pascals is what they're trying to confirm here, directly or indirectly, depending on where your reference is. But I think they're trying to expand that in 2.0. But if you got a good separation, then you do not have to have an exhaust fan. It's either or. So you are providing, have to confirm the test flows of your whole house ventilation, which means commissioning. So I do need to make sure that I have the correct flows in these, and that your outdoor inlets are located 10 feet away from contaminant sources. Many people believe that the exhaust that comes out of these are a contaminant source. Every community is a little different on that, because there are some centrifugal combined exhaust and intakes that can be used. So it depends on if your area is requiring that these must be separated by 10 feet in a distance, sometimes not below windows. There's a variety of simple requirements. It's kind of what it's asking you to make sure you know where this is exhausting and intaking. So there is a, how to find these emission projects link. It's here on the slides. We'll send these out as a PDF. And then it basically says in a long verbatim thing that we're not liable for VOCs and complex things involving what's going to, hurt you, kill you, or may not really cause much of an issue. And it's all being resolved and still working on, and third-party programs may be a resource for this. But I can tell you that coming up here, 2.0 moves this into a whole nother level about VOCs and emissions from the materials, because right now they're saying, we want you to be aware of and try and use some of these programs that are out there, but it's not easy to do. We're kind of able to work with you, but 2.0 will clearly put a path that you will either be able to comply or step up your game as to where you're going to get your materials from.
And just to be clear, we're referencing version 2.0 of the Indoor Air Plus program. This version has not been released yet. We're kind of giving you a heads up of what's coming. So when you're trying to meet your code obligations and utilize the Indoor Air Plus program, you're still using version 2, I believe it's
1.4 or something like that. So
yeah,
right. Right.
Yeah, version 4 of the program 1.
Right. So again, coming your way, and I did actually talk to these guys just about a week ago, and they're like, well, it may come out this year and it may not. Then you'll know that it's going to come out fairly soon, because they're going to do a second round of comments. They'll be like, okay, we finally figured out what we can and can't do based upon our restrictions. And so the second set of comments will come out, and then it'll probably be 6 months or worst case, a year after that. But so this is telling you that 2.0, again, not yet out, but you will be required to have some type of balanced ventilation system. And here's kind of on the second line showing you that you could get away with, making up your own balance concept with, plus or minus 10% or 10 CFM. But in general, there's lots of builders now that just accept that this is the future. There's lots of things that we didn't do a long time ago, and now we do. Kitchen exhaust almost always now go outside. 5 years ago, that wasn't even the case. So let's just accept that this is our future and figure out a way to get ahead of the curve and do it well early in the stage. So this is it. So your outdoor pass-through now requires a MERV 13. The supply and airflow measured flow are required, and you can use tab reports. But in general, they're saying if you're going to install something, we want to know really what was installed and how it was measured. And here you're actually seeing an external filter box. So you can see that they actually have a charcoal and 2 levels of filtration here. And I think if you're going to do something, you should really be thinking about controlling your own filtration pathway yourself, and just buy a filter box and work it into your system so that whatever's coming in, you have control over it. You're not paying $130 for a very small filter. We are now headed towards bathroom and kitchen exhausts in terms of requirement and controls. And, you're required for bath fan is to run for 30 minutes after or until your humidity stops. So usually these things happen and people are like, how do I do that? And the manufacturers step up quickly to be like, here's your solution. It costs $10 more, but this is the stat or the switch that you're going to put in. A lot of manufacturers are already included sensors into their switches. So these things will be a small hurdle by the time it actually is released. So, yep, that's fine. So you do have to have certain things. So we are stepping up our filtration to our duct systems to a MERV 13. And the issue that they didn't stress here, which I highly encourage you to do, that you will making sure you have low static. And notice that this filter's actually got little
Weather stripping.
Thank you. Yeah, weather stripping on the top and bottom, which makes it a good seal because it's the bypass that actually compromises these systems. So, but yeah, so you can use a non-13 during construction, but you need to step up your game and step up your design of your return to make sure you don't have high static that will compromise your system. This is an advisory, like I mentioned a second ago, that when you are dealing with these non-ducted systems that don't have an ability to filter, that right now it's an advisory. I told them they need to just, make at least remind people, just get one. They're not that expensive. Get a standalone portable air cleaner or something that's able to provide filtration in the house. So if you're a builder, this would be a great housewarming gift. I got you something. It's a CADR. CADR is the thing you're after. All right. High CADR will be a good filtration system. Here's the one that you should definitely pay attention to more than others. I have a feeling this will be in, it's not confirmed, high priority that your emissions will have to go through this CDPH standard, which is the California Department of Public Health standard. And darn near anything and everything you'll probably have to put in your house will have to comply with this type of concepts. So it's a VOCs, and all kinds of other materials will be approved or have already met this standard by the time it comes out. So you'll be very familiar with CDPH and come up with other acronyms around it because of the challenges that it may actually do. And here's some examples of the types of materials that you'll actually have to comply with. They have a whole thing about flooring, and different materials all have maybe an alternative to the CDPH, but in general, there's a lot of those in there. Before I give you out your top 5 as the things to ask, I do want to give you a few things. If you are going to do compliance pathway, that these big, huge hoods that many of people may own, the Alinors, the Testo hoods that are, 3 feet tall and whatever, they're really not able to do compliance. You really need something that's either like and they're not cheap, the Flow Finder that Retrotech sells. That's a $3,000 unit, but it's powered. There are some other ones that are out there. Yeah, there you go. Well done. That was very fast. So that is actually a powered flow hood. It's the only one out there on the market right now. There are some other ones, and the challenge is that it can go down to 10, 15, even 20 CFM. A lot of them are not able to really read something like that. But some other ones that are out there is it's called the Easy Hood from CPS. It's affordable. I think it's under $300-$400. It does okay, especially if you don't add the hood to it. You probably could get away with something that's less than $500 to actually measure these. All right, you want to do the top 5? And tonight's top 5 will be coming to you from Robby. Robby, give us your top 5.
So what type of core and what efficiency is your system going to need and have for your particular climate and house construction? How does it work with cold weather, which is obviously your main climate concern? What is the best distribution system for my project? What are the filtration options? And how easy is it, I guess, to put additional filtration onto the system that Joe was just showing us. And who will ultimately install and commission the system? That is crucial to the overall performance of the system. And we want to always make sure not only is it there, but does it work as it's been installed? And you can't know that unless you measure it or commission it.
So there were a couple questions that were out here, and I said we would make sure we address these, and there may be more coming in, I hope. One is from Christopher, says, can you confirm the efficiency and humidity of an ERV for Climate Zone 7 at Summit? And the reality is we cannot. And at this point, we're trying to deal with an engineer level of the person who manufactures that unit. All of them have people that will help you figure out what unit you need and confirm the conditions you're installing it in. And many of them also have people that will help you engineer it. I know Zender, if you want to buy a system, which will, it's not by no means the cheapest on the market, they will actually design your whole system for you and give you an entire parts list, all included in what you're trying to do. So I wish I was capable of saying, oh, yes, this is what you need and the capacity, but that is beyond our scope, especially off the top of our head.
Joe, if I can just kind of jump in, I wonder, more generally speaking, I wonder if his question was more general, like, do ERVs work in Climate Zone 7?
Oh, yeah, they do. People are installing them in Alaska now. So I think the challenge would be like, can HRVs actually maintain a place in the market is what we're trying to find. And that there was this, oh, where do you live? No, you need to use that. And, I go to with, if you guys know, construction instruction down in Denver, those guys are on top of their game in terms of analyzing what's going on. They evaluate a lot of systems, and their general rule of thumb is that, here in Colorado, an ERV is what you need.
Thanks. And just for everyone's reference, because I always keep the code book next to me, Alaska is both Climate Zones 7 and 8. So in fact, it can be colder there.
I think we answered the noise. There was another one here from Christopher. Go ahead. Yeah.
Well, you'll often see installations where the ERV or HRV is hung to help reduce vibration and whatnot. But from a noise factor, it's really how well the ducts are run. If you're going to hear the noise of the air moving across the diffuser, either when it's exhausting or being supplied. So just like all HVAC, it's important to not forget the diffuser and supply registers that you're installing in the system, because that will impact the noise of the air actually moving across the system.
So other ways to think about it, and Robby and I talked about it, one of the challenges that you need a lot of people who are used to installing this types of ducts in order to really make sure it's installed, not just to get the flow, but again, to reduce your noise. So you may get better flow if you're adding, metal duct that's insulated, but now you have a greater noise challenge. So there's usually a combination between flex and metal to get the longer runs, low friction, and you're using flex to go into the register and into the unit in a variety of ways. So you're trying to reduce that vibration that's happening, but it's not something that is you always can't confirm. If you didn't use something that actually was designed to reduce the noise, you may find out at the end that you should have added something like that. And make sure you have access to some of these manifolds that once they're in, because you're going to find out that, oh, something is clogged, something's loose, I got the wrong duct on the wrong manifold. Those kind of things all come out in commissioning at the last day.
Yeah. And I just wanted to point out that it does appear that the manifold systems are quieter and have been easier to some extent to commission and to ensure that you have the right balance of flow there.
Awesome. Well, so we are up at time, and I know there are a few more questions that have come in. So I have copied all the questions down, and I will send them to Robby and Joe to get their answers so that we can send them out with the slides and the recording. So is there anything, Robby and Joe, that you'd like to say before we sign off today?
Go ahead. I just saw one. Yeah, I saw one that talked about even an older home, you can fix the envelope. You can get older homes tighter by either manual Dillench or actually using aero barrier. So if you need to get there, we're encourage you have to get your envelope tight.
Yeah, and it's super important when you're talking about existing homes and working on them to think about ventilation, not just adding insulation or tightening the envelope. Here's our contact information. If anybody wants to reach out to us directly, more than happy to have conversations. We're also willing to stay on, Jess, if you wanted to go through those questions.
Okay. Yeah, great. That would be great. So if anyone wants to stay, we've got more time with Robby and Joe. Otherwise, I will send the recording out as a reminder. So if you want to just, when you get it, you could just click ahead to the Q&A portion and find out what they have to say. So if you need to jump off, thanks for joining us. And if you can stay, we'll be here answering your questions.
Do you know which one that we might not have answered?
Well, there are a couple came at the end, one of which is the people that are humidifying their houses. How well does this system work with that? I guess it depends on how they're humidifying would be the kind of follow-up. I'm assuming it'll be if you don't have a duct system, then you must have some standalone humidifiers is what I'm assuming there indirectly.
Okay, yeah, and I'm just scrolling through here. So do you know how common it is in other municipalities and counties, and let's say across Colorado, to require HRVs or ERVs?
There's no jurisdiction that I'm aware of that requires specifically HRVs or ERVs. Boulder County does require balanced ventilation, but you can meet that requirement in other ways. For, like Joe was explaining earlier, you could have an exhaust fan and a supply fan meeting that balanced requirement. So no.
Minnesota, I know it's not Colorado, but Minnesota has required this, again, balance concept for many years. And they realize, and Canada, they just realize that it's a better way to control the thermal bridging of the envelope. All the things that happen with the envelope, I'm now able to control this because I have a balanced system. I'm not creating infiltration, which only compromises so many things about durability and comfort.
Yeah.
And then I don't know if you guys saw this one. I don't think we did answer it, but what triggers the defrost mode? So Chris lives in Blue River, which is really, it's like the cold pocket of Summit County, and has 54 out of 60 days where he's had single digits for over 10 hours a day. And so then how much is the efficiency and air movement impacted? And do you know how much testing has occurred with these systems in climate zone 7?
I know every manufacturer has tried to address this, and they're hoping the day when the code says everybody put something like this in. So I think they're trying to be ready for that. It may not be a defrost cycle is your best choice of a unit. Maybe there's something that does have a preheater and worst case, a backup defrost mode is what I would be. If I was living there, I wouldn't be determined that I'm waiting for things to defrost or just go into exhaust or off mode. I would probably be more proactive with the heater.
Yeah, it's usually triggered, I believe, by the a temperature sensor in the unit for the incoming air there.
Great.
There was another question that I saw that I thought was interesting with regards to code allowing exhaust air from kitchens and bathrooms to be taken through the ERV. And yes, code will allow that. It's more based on the CFM rate that's coming from those locations. So as Joe is saying, 20 CFM, 20 CFM continuously from bathrooms, 50 CFM intermittently from bathrooms, and then 100 CFM from kitchens.
Well, that's 100 is intermittent. If you want to be continuous, you need to show that you're complying with 5 air changes per that kitchen volume.
Yeah.
Of CFM.
as Joe also mentioned, it's not recommended to use the ERV for the kitchen because of the additional grease and other things that you'll be exhausting out of that system. So the kitchen hood is still the primary recommendation, ducted all the way to the outside, minimum 6-inch duct with limited bends to make sure that you're getting that exhaust air from your kitchen out while you're cooking. There.
Thanks. And I just wanted to highlight that Matt just typed in a comment to remind us all that HRVs and ERVs aren't actually required. You know, he says it's one of the more cost-effective ways to meet the target score for the Zero Energy Ready Home program. So, you know, no one is mandating it necessarily, but you might find that it is beneficial to your project for meeting your HERS score. Your target HERS score.
Yeah.
The one thing that if you're still here, you know, we still have 28 people, that if you wonder where we're going to be in just a couple of years, it's going to be, oh, okay, I now need to figure out how to install these better, because this isn't going away. This isn't like a fad, like, oh yeah, well, vinyl siding, you know, even kind of came back, but you know what, we moved on to other better products. This is something that will be implemented in all homes as we move forward.
Great, thank you.
So there's a question, can you confirm the efficiency and humidity of the ERV for climate zone 7? I mean, I think we can give you a range of efficiency that, you know, that's based off of the HVI rating there. But, you know, ultimately it depends on how well it's installed and matched to the house that it's being installed in. And in climate zone 7, again, it can help maintain the indoor humidity level in the house. It's not going to add or supplement that humidity level in the house.
Great. So I think that's it. There's one final question that's asking about continuing education credit. And to be honest, we didn't get asked about this until earlier this week. So I'm going to have to look into what AIA requires, and we can certainly try. Yeah, thanks, Joe. Yes, I was told earlier this week that it is quite a process, so no promises. But
you can probably get that through Erica DeLello.
Okay, I will ask Erica, and we'll get back to you all on that. So yeah, thank you all. Again, I don't see any additional questions. So as Robby mentioned, you've got their contact information on the screen here. And then I will be sending out the recording and slides. And then we also have a survey for you all. And as a reminder, if you have any requests for topics for future workshops, please let us know. Happy to accommodate. And hope to see you all in person on March 30th when Robby's coming back to talk to us all about continuous insulation.
Great. Just a quick shameless plug for the BuildCast. Check out the podcast on your favorite platform.
I'm on there. Go listen to my podcast.
Awesome. All right. Thanks to Robby and Joe for joining us today. Thanks to all of you for attending. And like I said, hope to see you all in March. Have a great day.
Great.
Thanks, everybody.